Taylor's theorem. Convergence of Taylor series. We've learned that the Taylor series of f centered at x0 is the sum from k equals 0 to infinity of the kth derivative of f evaluated at x0 divided by k factorial times x minus x0 to the kth power. Such a series can always be constructed assuming that the kth derivative at x0 exists for all k. The question we want to address is, when does this series converge to f of x? In other words, what do we need to assume about the function f in order that the Taylor series of f actually represents f on an interval containing x0? This is a very important question because it is possible that the series converges only at x0. Also, it is possible that the series converges for all x, but equals f of x only at x0. We'll not provide an example of the first situation here, but there is a relatively simple example of the second fact. Let f of x equal e to the minus 1 over x squared if x is not equal to 0, and 0 if x equals 0. Here's the graph of the function f. Notice that the graph is extremely flat near x equals 0. It even looks as if it's constant on some interval surrounding 0, but in fact the function equals 0 only at x equals 0. If we zoom in on the graph, it still appears to be essentially constant on an interval around 0. In fact, no matter how far we zoom in on this graph, it will look essentially like this. Now it turns out that the kth derivative of this function evaluated at 0 is equal to 0 for all k. This is basically because every derivative of e to the minus 1 over x squared looks like e to the minus 1 over x squared times some rational function of x, which will always approach 0 as x approaches 0. This tells us that every term in the Taylor series for f about 0 is equal to 0. And so the Taylor series for f about 0 is 0 for all x, while f of x is equal to 0 only at x equals 0. So here we have a Maclaurin series for a function f that converges for all x, but equals f of x only at x equals 0. This demonstrates that the convergence of a Taylor series for a function f on an interval surrounding x0 is not enough to conclude that the Taylor series converges to f of x on that interval. So we have to be concerned with more than just the convergence of the series. We have to be concerned with what it converges to. Taylor polynomials. The nth Taylor polynomial, centered at x0 for a function f, is t sub n of x equal to f of x0 plus f prime of x0 times x minus x0, and so forth, up to the nth derivative of f evaluated at x0 divided by n factorial times x minus x0 to the n. These are just the terms of the Taylor series up to the degree n term. This is the polynomial whose derivatives up to order n agree with those of f at x0. In that sense, it provides the best local approximation of f of x near x0 by a polynomial of degree less than or equal to n. Example, let f of x equal e to the x. Then the kth derivative of f is equal to e to the x for all k. And so the kth derivative of f evaluated at 0 is equal to 1 for all k. So the first several Taylor polynomials centered at 0 for e to the x are t0 of x equals 1, t1 of x equals 1 plus 1 times x, t2 of x equals 1 plus x plus 1 half x squared, t3 of x equals 1 plus x plus 1 half x squared plus 1 over 3 factorial x cubed. T4 of x is just T3 of x plus the additional term 1 over 4 factorial x to the fourth, and so on. Now let's have a look at the graphs of these compared with the graph of e to the x. Here's the graph of T1 of x. That's just the graph of the linear approximation to e to the x at x equals 0. Here's the graph of T2, followed by the graph of T3, the graph of T4, then T5, T6, T7, T8, T9, T10, and finally T11. Notice that each of those in turn gave a good approximation to e to the x over a wider interval. Now we already know that the Maclaurin series for e to the x converges to e to the x for all x. So these polynomials will eventually approximate e to the x as well as we like over an interval as wide as we like. Another example. Let f of x equals sine x. Then f prime of x equals cosine x. F double prime of x is minus sine x. F triple prime of x is minus cosine x, and the fourth derivative is sine x, and thereafter we cycle through the same four functions. So the numbers f of 0, f prime of 0, f double prime of 0, and so on are 0, 1, 0, minus 1, 0, 1, 0, minus 1, and so on. Thus the first several Taylor polynomials centered at 0 for sine x are t0 of x equals 0, t1 of x equals 0 plus x, t2 of x equals 0 plus x plus 0. So notice that t2 and t1 are the same. Since the third derivative equals minus 1 and the fourth derivative equals 0, t3 of x and t4 of x will both equal x minus 1 over 3 factorial x cubed. Similarly, t5 of x and t6 of x are both x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. Now let's compare the graphs of those with the graph of sine x. Here's the graph of t1 of x. That's the linear approximation to the function at 0. That's also the graph of t2 of x. Here's the graph of t3 of x, which is also t4 of x. Here's the graph of t5 of x, which is also t6 of x, and so on. And we'll stop with t19 of x. So again, notice that we get better and better approximations of sine x from these polynomials over wider and wider intervals. The remainder term. Define the nth remainder by capital R sub n of x equals f of x minus the nth Taylor polynomial t sub n of x. That is, f of x equals the nth Taylor polynomial t sub n of x plus the nth remainder r sub n of x. Then, the limit as n goes to infinity of t sub n of x will equal f of x if and only if the limit as n goes to infinity of r sub n of x equals 0. Let's look at the graphs of the first several of these remainders in the case of the sine function. Here we see the graph of sine x along with the linear approximation, which is t1 of x, and the blue graph is the remainder r1 of x. That's just the difference between sine x and its linear approximation at 0. Notice that the remainder is very close to 0, where the Taylor polynomial provides a good approximation of sine x. Here's the graph of sine x along with the third Taylor polynomial and third remainder. Here's the fifth Taylor polynomial and the fifth remainder, the seventh Taylor polynomial and the seventh remainder, the ninth Taylor polynomial and the ninth remainder, and the 11th Taylor polynomial and 11th remainder. So at each x, as the value of the Taylor polynomials approach sine of x, the value of the remainders are approaching 0. An important remark: this isn't necessarily the same as the remainder associated with the partial sums of the Taylor series, since they might not converge to f of x. In other words, when we've previously discussed the remainder associated with a series, it was defined as the difference between the partial sums and whatever the series happened to converge to. Here we are specifically looking at the difference between the partial sums of the Taylor series and the function f. Now we're ready to state Taylor's theorem. Suppose that f, f prime, and so on up to the n plus first derivative of f are continuous on an interval I centered at x0. Then, for any x in I, the nth remainder r sub n of x is equal to 1 over n factorial times the integral from x0 to x of the n plus first derivative at t times x minus t to the nth power dt. Note that this is an exact and computable expression for the nth remainder. However, if one actually does the computation for a given n, it will simply end up being f of x minus the nth Taylor polynomial. So it does not have a great deal of practical value in and of itself. It is, however, a very important theoretical result that leads to the following corollary, which is a bit more useful from a practical point of view. For some number c between x0 and x, the nth remainder, r sub n of x, is equal to the n plus first derivative of f evaluated at c divided by n plus 1 factorial times x minus x0 to the n plus 1 power. This is known as Lagrange's formula for the remainder. Now we're going to give an outline of the proof of the integral form of the remainder. By the fundamental theorem of calculus, the integral from x0 to x of f prime of t dt is equal to f of x minus f of x0. And rearranging gives f of x equal to f of x0 plus the integral from x0 to x of f prime of t dt. Now, f of x0 is just the zeroth Taylor polynomial centered at x0, and so the second term there is exactly equal to the zeroth remainder at x. And notice that integral is exactly the form of the remainder stated in the theorem when n is equal to 0. Now we're going to integrate repeatedly by parts. Let u equal f prime of t, which makes du equal f double prime of t dt, and let dv be dt, which gives us v equal to t. But we could also add any constant to v, so let's write v as t minus x, since x is fixed as far as the integration is concerned. Now that equals minus x minus t. And so integration by parts tells us that the integral from x0 to x of f prime of t dt is equal to u times v evaluated between t equals x0 and t equals x, which is minus f prime of t times x minus t evaluated between x0 and x, minus the integral of v du, which here is plus the integral from x0 to x of f double prime of t times x minus t dt. Now let's perform the evaluation in the uv term. That term is equal to 0 when t equals x, and equals f prime of x0 times x minus x0 when t is x0. So that term becomes plus f prime of x0 times x minus x0. Now notice that the first two terms here on the right-hand side constitute the first Taylor polynomial t1 of x. Therefore, the third term is precisely the first remainder r1 of x. And notice that it has exactly the form claimed in the theorem when n equals 1. Now let's integrate that remainder term using integration by parts again. Let u equal f double prime of t, which makes du equal f triple prime of t dt, and let dv equal x minus t dt, which makes v equal minus 1/2 of x minus t squared. So now we have the same first two terms as before, plus u times v, which is f double prime times minus 1/2 x minus t squared, evaluated between t equals x0 and x, minus the integral of v du, which is plus 1/2 of the integral from x0 to x of f triple prime of t times x minus t squared dt. Now when we do the evaluation of uv between the endpoints, that term becomes plus f double prime of x0 divided by 2 times x minus x0 squared. Notice that the first three terms here are the Taylor polynomial t2 of x, and so the integral term is precisely the remainder r2 of x. And again, that remainder has exactly the form stated in the theorem, this time corresponding to n equal to 2. Now if we continue this, after n steps, we will have f of x equal to f of x0 plus f prime of x0 times x minus x0 plus terms up to the nth derivative of f evaluated at x0 divided by n factorial times x minus x0 to the nth power plus 1 over n factorial times the integral from x0 to x of the n plus first derivative of f at t times x minus t to the nth power dt. The terms in the first line on the right-hand side are precisely the nth Taylor polynomial t sub n of x, and so the integral term on the second line must be the nth remainder r sub n of x. which is exactly what we wanted to show. Now for the Lagrange formula for the remainder. We begin with the integral form of the remainder, which we've just proven, and we're going to apply a result that's called the mean value theorem for integrals. It states that for continuous functions f and g on the interval a, b, the integral from a to b of f of x times g of x dx is equal to f of c times the integral from a to b of g of x dx for some number c in the open interval from a to b. In the special case where g of x is equal to 1 for all x, this says that the integral from a to b of f of x dx is equal to the average value of f over the interval ab times b minus a. Now, by applying the general mean value theorem for integrals to the integral form of the remainder, we find that r sub n of x is equal to the n plus first derivative of f evaluated at some c between x naught and x divided by n factorial times the integral from x naught to x of x minus t to the nth power dt. Now we can evaluate that integral, and when we do, it becomes 1 over n plus 1 times x minus t to the n plus 1 power evaluated between x naught and x, which equals 1 over n plus 1 times x minus x naught to the n plus first power. Now, since n factorial times n plus 1 is just n plus 1 factorial, we have r sub n of x equal to Lagrange's formula for the remainder. Example. Given that e is less than 3, estimate the error in the approximation of e by the sixth Taylor polynomial T6 evaluated at 1, which equals 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, and so on up to 1 over 6 factorial. We want to estimate the sixth remainder evaluated at 1, which is e minus T6 of 1. Now we know that the seventh derivative of f is just e to the x, and so using Lagrange's formula for the remainder, we have that r6 of x is equal to e to some power c divided by 7 factorial times 1 minus 0 to the 7th power, or simply e to the c divided by 7 factorial, where the number c is strictly between 0 and 1. Now, since c is between 0 and 1, e to the c is greater than 1 and less than e to the first power, which we assume we know is less than 3. So we have r6 of 1 greater than 1 over 7 factorial and less than 3 over 7 factorial. That lower bound is approximately 2 times 10 to the minus 4, and the upper bound is approximately 6 times 10 to the minus 4. So we have both a lower bound and an upper bound on the remainder. Now it turns out that T6 of 1 is equal to 2.7180555 and so on with the 5's repeating, so we know that E is greater than that number plus the lower bound on our remainder, which is about 2.71825 where we've rounded down, and less than that number plus the upper bound on the remainder, which is about 2.71866 where we've rounded the last digit up. The exact value of E, you may recall, rounds to 2.71828, so E is actually closer to the lower bound than it is to the upper bound in this inequality. Under the same assumptions as in Taylor's theorem, from Lagrange's formula for the remainder follows corollary 2. Let x be an I, and let j be the closed interval from x naught to x if x is greater than x naught, and the closed interval from x to x naught if x is less than x naught. Then, the absolute value of the remainder, r sub n of x, is less than or equal to the maximum value over the interval j of the absolute value of the n plus first derivative divided by n plus 1 factorial times the absolute value of x minus x naught to the n plus first power. Remark: if the Taylor series for f about x naught is an alternating series with terms that decrease in absolute value, and if that series converges to f of x, then we already knew that the absolute value of r sub n of x is less than the absolute value of the n plus first term in the series, which is the absolute value of the n plus first derivative at x naught divided by n plus 1 factorial times the absolute value of x minus x naught to the n plus first power. Now notice how similar that upper bound is to the upper bound stated in Corollary 2. In fact, they are exactly the same in the case where the maximum value over j of the absolute value of the n plus first derivative occurs at x naught. Example. For f of x equal to the natural log of x, the third Taylor polynomial centered at 1 is t3 of x equal to x minus 1 minus 1/2 of x minus 1 squared plus 1/3 times x minus 1 cubed. Find an upper bound on the error in approximating the natural log of 1.2 with t3 of 1.2 using A, Corollary 2, and B, the remainder estimate for alternating series. Now in both parts we want to estimate the absolute value of the remainder term R3 of 1.2, which equals the absolute value of the natural log of 1.2 minus t3 of 1.2. To use Corollary 2, we need to have the fourth derivative of the natural log of x, so we start with the first derivative, which is x to the minus 1, and then differentiate 3 more times until finally we have the fourth derivative, minus 6x to the minus 4. So the absolute value of the fourth derivative is 6 over x to the fourth, which is obviously a decreasing function on the closed interval from 1 to 1.2. So, for all x between 1 and 1.2, the absolute value of the fourth derivative is less than or equal to its value at 1, which is 6. Therefore, by Corollary 2, the absolute value of R3 of 1.2 is less than or equal to 6 times 1.2 minus 1 to the fourth power divided by 4 factorial, which turns out to be 0.004. Now, the Taylor series x minus 1 minus 1/2 of x minus 1 squared plus 1/3 of x minus 1 cubed and so forth converges to the natural log of x if x is greater than 0 and less than or equal to 2. We know this from the derivation of the series from the geometric series. The series is also an alternating series if x is greater than 1, and its terms decrease in absolute value for any x in its interval of convergence. Therefore, the absolute value of R3 at 1.2 is less than or equal to the absolute value of the fourth degree term in the series at x equal to 1.2, which is 1/4 times 1.2 minus 1 to the fourth power, which equals 0.004. Now notice that both methods gave exactly the same estimate in this case. The reason is that the maximum of the absolute value of the fourth derivative over the interval 1 to 1.2 occurred at the left end, point 1, which is the number about which the series is centered. Another example. Find a Taylor polynomial centered at 0 that approximates cosine x to within 10 to the minus 6 for all x in the closed interval from minus pi over 2 to pi over 2. Since all of the derivatives of cosine x are either plus or minus sine x or plus or minus cosine x, we have an easy estimate on the absolute value of all derivatives. The absolute value of the kth derivative of cosine x is less than or equal to 1 for all x and all k. So Corollary 2 says that the absolute value of r sub n of x is less than 1 over n plus 1 factorial times the absolute value of x to the n plus first power for all x. So if x is between minus pi over 2 and pi over 2, then the absolute value of r sub n of x is less than 1 over n plus 1 factorial times pi over 2 to the n plus first power. Now computation shows that 1 over 11 factorial times pi over 2 to the 11th is approximately 3.6 times 10 to the minus 6, and 1 over 12 factorial times pi over 2 to the 12th power is roughly 4.7 times 10 to the minus 7. So we want n plus 1 equal to 12, that is, n equal to 11, and the desired polynomial is t sub 11 of x, which is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th, and so on up to minus 1 over 10 factorial times x to the 10th. Now let's finish here with another corollary on the equality of a function f with its Taylor series. Let's suppose that f is infinitely differentiable on the closed interval from x0 minus r to x0 plus r, so in particular f has a Taylor series expansion about x naught, and let capital M sub k equal the maximum over that interval of the absolute value of the kth derivative of f for k equal to 1, 2, 3, and so on. Now by corollary 2, if the absolute value of x minus x naught is less than or equal to r, then the absolute value of the kth remainder at x is less than or equal to capital M sub k times the absolute value of x minus x naught to the kth power divided by k factorial, which in turn is less than or equal to capital M sub k times little r to the k divided by k factorial. So, if the limit as k goes to infinity of capital M sub k times little r to the k divided by k factorial equals 0, then the Taylor series for f centered at x naught converges to f of x for all x in the closed interval from x naught minus r to x naught plus r. Now notice that capital M sub k times r to the k divided by k factorial is the kth term of a sequence, and because of the k factorial in the denominator, that sequence will tend to 0 for any r provided that capital M sub k does not grow too fast. Also, if r is less than 1, then the r to the k factor actually helps the sequence converge to 0, again, provided that capital M sub k does not grow too fast. So let's note that the condition, limit as k goes to infinity of m sub k times r to the k divided by k factorial equals 0, will be true if, for example, the sequence capital M sub k is bounded, which is true for functions like sine x, cosine x, e to the x, for any positive r. And note that this is exactly the assumption that we made in the previous lecture when we assumed that there was a bound on capital M sub k that was independent of k. The sequence m sub k times r to the k divided by k factorial also converges to 0 if the sequence m sub k grows exponentially. That's because any number to the kth power divided by k factorial will approach 0 as k goes to infinity. Capital M sub k grows exponentially for functions like sine 2x, cosine 10x, e to the 3x, and so forth. In particular, for e to the 3x, each differentiation produces another factor of 3. In fact, the kth derivative would be 3 to the k times e to the 3x. The sequence m sub k, r to the k divided by k factorial, will also approach 0 if r is less than 1, and the sequence capital M sub k divided by k factorial is bounded or grows like a power of k. That allows m sub k itself to grow as fast as k factorial, or even a power of k times k factorial. This situation arises for functions related to the geometric series, such as the natural log of 1 plus x, the inverse tangent of x, and so forth. So all of this means that, unless the sequence m sub k grows faster than any power of k times k factorial as k goes to infinity, the function's Taylor series will equal the function on an interval centered at x naught.